I'm Michele Reticcioli from P07 TACO project led by Cesare Franchini, and we work together with Victor and Marco. And what I would like to talk about today is polarons in TACO. Why we should really care about these polarons in the system that we investigate in this TACO cooperation. So I'm going to start with a very brief introduction on polarons in oxide, about their properties, and then move to some novel aspects that we have recently addressed. And then I will focus on the effect of these polarons in the materials, how can they impact the functionalities and applications. Finally, I will talk about some novel recipes that we are starting to use to simulate our polarons in TACO, that is the machine learning for the formation of polarons and for the dynamics of polarons. So let's start with this brief introduction. If we take a perfect crystal, an oxide semiconductor, we will have a perfectly filled valence band and a perfectly empty conduction band. And then if we dope the material or if we have defects in the material, we will introduce in the system some excess charge. It can be excess holes or excess electrons. Here I will just speak about excess electrons for simplicity, but you can have also holes in principle. And if you apply a simple rigid band model, then you will start to fill the conduction band and populate the bottom of the conduction band with electrons that are homogeneously dispersed in your system. They are equivalently shared by equivalent atoms in your system. But some materials are able to accommodate this excess charge in a different manner. They can get the charge localized on one specific site, which is surrounded by some local lattice distortion. So there is an excess charge on one side, and the lattice is deformed in order to accommodate this excess charge. And the density of state will look like a semiconducting density of state with a peak, the polaronic peak, in the energy gap. And this is actually, to be precise, what a small electron polaron looks like. But there are different types of polarons, but today I'd only refer to these specific ones. And this is just what I wanted to tell you about polarons as an introduction. And now I would like to introduce what we call intrinsic polarons. Let me explain what we mean by that. So if you take a compound that has some rather strong ionic bonds, then you can describe this system with cations and anions. This is a perovskite potassium tantalate, similar to what Michele has already introduced. You can think about this material as built by a stacking of layers that are alternatively positively and negatively charged. In addition to this, you can also describe this stacking as given by a net transfer of charge from one layer to every adjacent layer. In this case, in this material, the tantalum oxygen layer will donate half electron per unit cell to the layer above and below. So then when you move to the surface, you have this stacking of positively and negatively charged layer till you reach the surface. At the surface boundary, this charge transfer cannot occur anymore. So then you have some amount of charge that needs to be accommodated somehow by the system. And this is what we can consider as an intrinsic excess charge. As Michele mentioned, this will be called the polar surface, and there will be much more to talk about in terms of stability of the surface. But if you are very careful, you can cleave your sample and obtain a rather flat surface that is shown, for example, in this AFM experimental image that shows terraces of potassium oxygen alternated to terraces of tantalum oxygen 2. And these are given by having the cut done above or below the tantalum oxygen layer. So this can be stabilized in the experiment. And if we focus now on the tantalum oxygen layer, we have, or terrace, we have this excess of electrons that we need to accommodate somehow. Conventionally, we have this model of the two-dimensional electron gas, 2DEG, where this charge is distributed over the surface and some shallow layers below the surface. It occupies the bottom of the conduction band, and then layers that are deeper down are not affected by this intrinsic excess charge. But we can instead obtain the transformation of polarons in this system, which is now driven not by defect or doping, but just by the intrinsic charge of the material. So it's an intrinsic properties now of the material, and this allows us to, for example, study the properties of polarons without having to account for the interaction with external agents like defects in the material. Now I'd like to introduce this concept of the polaron configurational space. This is very similar to something that has been discussed already for the structure of the surface. In fact, this polaronic states can localize on different sides. So it's always going to be a tantalum atom in our case, but can be different ones. And because these particles interact with each other, via, for example, electrostatic interaction, or if they are very close to each other with Pauli repulsion, or because of the distortion they make around themselves, then different configurations lead to different energies. And it's important to explore many different polaronic configurations in order to identify the polaronic ground state. And unfortunately, we are still doing this by hand. But nevertheless, by doing this by hand, so trying different polaronic configuration, we obtain something that is called bipolaron. So in this case, we have a tantalum side that is reduced twice, so from 5 plus to 3 plus. It has two polarons, and you can clearly see this in-gap peak that characterizes the polarons. Also, for bipolarons, you have to find the right arrangement that gives you the best energy, the more stable configuration, which is this one, along, where the bipolarons are all on the surface and arranged along the 110 direction. And this is not the end of the story, because you can go further and obtain mixed configurations of polarons in the surface and subsurface and bipolarons. And in this way, you can minimize the interactions and obtain even more stable configurations. And then you can also have a completely different electronic reconstruction. This is a charge density wave, where now the charge is distributed more likely a two-dimensional electron gas, with the difference then the charge is not homogeneously distributed. There is a charge modulation. Here there is a simulated STM image where you have some bright spot alternated to darkest spot in a square root of 2 pattern. Also, you have the appearance of a very shallow and broad peak at the bottom of the conduction band, with the tail going through the Fermi energy. So the electronic phase is very rich on the surface of this polar surface. We can also obtain solution where polarons are coexist with the charge density wave, and this will be the dose. And then we move to the comparison to this with the experiment. Actually, the experiments here motivated all of this work, where we obtain from this spectroscopy data here a shoulder below the Fermi energy that identifies the charge density waves, and then some in-gap states that are identified as polarons and bipolarons. And by doing an STM scanning of the samples, here what you have is that the KO terraces appear black because we are looking at the field state, and there is no field state on the KO terraces. So, but our focus is on the tantalum oxygen 2 terraces, and you have at this low voltage the appearance of this charge modulation, while at deeper voltages you get these localized states. So at least qualitatively, there is a good agreement between all the different phases obtained in the FT and with the experimental observation. Why do we care about these intrinsic polaron? Because if they are there, just as an intrinsic property of the material, then we can expect that they impact some functionalities. And here I would like to focus on catalysis. In this case, in the experiment, a full monolayer of CO was deposited on the sample. So now we don't care about the KO terraces. We focus on the tantalum oxygen 2 terrace. And here we observe two types of signal from our AFM images, a bright spot and a dark spot. The dark spots are actually aligned more or less along the 110 direction. And we can try to simulate this in DFT and obtain that actually very good, the most stable solution will be the bipolarons arranged along this 110 direction, hybridizing with the CO molecules on top and affecting the properties of the CO, while the other CO on the terrace are not affected by this excess charge. Okay, if we look a little bit more in detail, we will have that this hybridization elongates a bit the bonds of the CO molecule. So this means that the bond is a bit softer, and this is why it appears black, the CO molecule on these spots, with respect to the other COs that are not actually modified by the charge. It would be also interesting to show another effects of polarons on this material, that is reversal of the ferroelectricity polarization, but I don't discuss this now because I want to move to these novel recipes for polaron tacos. So how can we model these polarons? How can we explore this configurational space of polarons without having to do everything by hand? First of all, I'd like to discuss the dynamics. You surely all know this on-the-fly machine learning force field model developed in Georg's group, Georg Kress's group, where basically starting from purely structural information, you can extract the material properties and study the evolution of the material in time. What you do is you start from a given position of your atoms, you activate your machine learning force field, and that, which gives you the forces. You also are able to estimate the error accuracy of this prediction. If the accuracy is small, or if the error is big, then you don't believe your model and you turn on DFT, which is more expensive but more accurate. Instead, if the predictions are good, then what you do is to update the position of the atoms according to the forces given by your machine learning. And then you repeat this. This works pretty well, but we think that in order to include polarons in your system, in order to study a polaronic material, you will need to explicitly take into account the charge. So you will need to tell to this model also where the polaron is before you can calculate the forces and the material properties. In fact, polarons, when they are thermally activated, they can hop from one side to another one, so their position is not fixed, but they get destabilized by thermal fluctuations around the localization site, and then they hop to another site. So we have tried to play around with a simple neural network moment, where we use as descriptor for our system a set of distances in terms of the localization site. So we take our polaronic site and we measure the distances with the first 6 or 8 neighboring sites. And just by using this little information, we can run a very quick and simple code to get the polaron localization. So if with the information whether the polaron is localized on this site or not, which is technically achieved by obtaining the magnetic moment. But this is more like technicalities. And the goal would be to take this model and put it in the force field scheme. So once we established that the error is not big, we could then try to apply this model and to identify the polaron formation, to identify whether thermal distortions are so bad that the polaron wants to hop away or remain on the side. And this was done by a student in our group, Dominic Feinberger. These are some preliminary results. It looks pretty good when you look at the magnetization given by the FT in blue. So something close to 1 means that the polaron is on this specific site under analysis. And then at a certain moment, the magnetization drops to 0 because the polaron has hopped away. And this simple neural network model is able to reproduce this behavior. And a similar model can be used also to identify the hopping probability. So given that we know that there is a polaron on one specific site, we want to know if in some steps in the future in our simulation, because of how bad the local distortions are now in this very moment, if in the future this polaron will hop away. And also in this case, it seems that we are able to predict with some enough in advantage if the polaron hops away or not. So this is the probability given by our model. When it goes to 1, it means the polaron is going to hop away. And in blue here is the magnetization on that side. So it's going to drop to 0. After a while, this hopping probability given by machine learning went up high. OK, then the other way to approach this problem would be to explicitly model many configurations in the FT, in a statical approach now, calculate the energy of every different configuration, give everything to a machine learning model, train this machine learning model, here's a kernel regression model, to obtain what? To obtain the polaron energy, so the stability for every different polaronic configuration. And thanks to this, we can identify maybe better polaronic ground state that we had before by just looking by hand to the various polaronic configurations. So in this case, Victor went from 500 to 500,000 configurations. But he's not satisfied enough, and he's already looking into better ways to solve this problem. That would be to use methods that do not rely on large databases from DFT, and also methods that can be more generalizable. And there is a poster of him in the poster session, so I leave all details to himself. So this is a summary of what I've discussed today, and the main take-home messages are that polarons in oxide can form for defects and doping, but they can also be an intrinsic properties in specific cases, such as the polar surfaces, and they have a huge impact on many applications. You really get different results when you take them into account or not. And finally, this is more a perspective of what we do in this TAGO P7 project, is that we like to introduce the machine learning in the problem of modeling polarons. And if you are curious about the polarons, the properties of polarons, I'd like to advertise this review that came up recently as from members and collaborators of our TAGO community. And with this, I'd like to thank all the collaborators from TAGO, so for the different projects of TAGO, like Ulrike and Michele, for the experimental part, maybe. Actually, the experiments were conducted by Zishan Wang in his visiting period in TU. also Gareth and Matthias for the interpretation of the catalysis data, and Georg and Carla for the discussion with regarding the machine learning part, and of course Dominic and Victor that perform all the calculations, and our external collaborator of the Tago project, Martin Seftin, that is now in Prague, and of course Cesare Franchini. And you for your attention.
Thank you, Michele. The talk is open for questions. Can I ask the first one? When you model these surfaces, do you add an extra charge, or they charge neutral cells?
Unbelievably not. This is, I don't add any charge. This charge only comes from the fact that this layer wants to be with a given valence state, so positively charged. And to do so in the bulk, it just donates half electron to the next layer. But here at the surface, there is nothing where this excess electron can go. So they remain there. They need to be somehow accommodated by the system itself. And the most efficient way will be this combination of polarons, bipolarons, and charge density waves. And usually this charge instead is treated as a two-dimensional electron gas. So if you take a 1-by-1 slab very, very deep, then you obtain a two-dimensional electron gas because the charge is constrained to have that symmetry. So you need to go to a larger cell in order to accommodate other possible solutions.
But isn't these different structures, or you could see these different polarons as different structures, wouldn't you be able to catch them with your descriptors, with your atomic descriptors? I'm asking for what's the need for this extra description of the local charge, if I understood you correctly?
You mean extra description? You mean via machine learning methods, or?
Yeah, the external. You could call it your external neural network.
Yeah. So the aim there is that a different polaronic configuration could lead you to a different impact of application. Imagine your polarons are more stable in deeper layers. They will not potentially affect at all your catalysis, for example, occurring on the surface. So you want to be very sure about where the polarons are, because depending on where they are, they can interact differently. And while I can try many different configurations by hand, maybe I miss something and I need some more efficient method to help me drive my exploration.
Are there more questions?
Yeah, can you comment a little bit on the new method, maybe taking out a little bit of air of Victor's poster that you said more transferable and.
Yeah, so this is something that's very similar conceptually as what we have seen today in the initial talk, right? Where you have a rich phase diagram, and you want to explore it and find the best configurations. In this case, it's polaron. It's not atomic structures, but conceptually something very, very similar. And the problem we have with this model is that we take into account as descriptors properties that are specific for this material that we investigated, that is titanium dioxide. And so what Victor would like to do is to find more generalizable descriptors, not something specific of titanium dioxide. He has already done some tests on strontium titanate, which work reasonably well, but the final aim is to go beyond this supervised learning scheme where you have a database, you train your model, and then you go to production and try to see if you find something. He would like to go towards some different approaches like those that were presented earlier today, where you have reinforcement agents while you try to explore your configurational space.
But you still need to train it for each material separately, right, or not?
But the method can be general.
Okay.
And this is something we don't know. Maybe in the frame of perovskites, you could imagine these polarons don't work too much differently from one perovskite to another one. So this is something we don't know, and it's an interesting aspect to investigate more in detail.
Okay. So if there are no further questions, we thank Michele again.
Thank you.